So good morning everybody. Welcome to my channel. So after long time again I start with videos. Today I am discussing the very important topic related to electronic configuration. There is some exceptional electronic configurations are present in periodic table. These exceptional electronic configurations are discussed not only in the periodic table, they are discussed in individual groups, especially in D block and F block. As for IIT advanced or mains point of view concerned, there is a compulsory question related to D and F block. D and F block, in which as the ultimate topic electronic configuration. D and F block ultimate topic is electronic configuration. There is some exceptional electronic configurations are there. So what is the meaning of exceptional? First of all, what is the meaning of exceptional? Yes, according to Abbo rule, Euler diagram is there in atomic structure. Yes, Euler diagram, according to Euler diagram, yes, if the species contain more than one electron, the species contain more than one electron, then how the electrons enter into the various orbitals? How the electrons enter into various orbitals? The total can be discussed in Euler diagram. Yes, we already know. After complete filling of 1s, the electron enter into 2s. After complete filling of electron, 1s subshell, the next electron enter into 2s. Yes, this is based on n plus L rule. This is based on n plus L rule. We know n plus L. N is a principal quantum number, L is a azimuthal quantum number. So this is n value 1. L value for S subshell is how much? 0. So therefore, L value is 0 for S subshell, L value 1 for P subshell, L value 2 for D subshell, L value 3 for F subshell. By using these n plus L values, we construct a Euler diagram. Yes, I think we already know. Euler diagram is completely depending on n plus L rule. After complete filling of lower energy, then only electron enter into higher energy, that is Abbo principle. This is based upon n plus L rule. What is n plus L rule? Yes, the subshell which has lowest n plus L value has lower energy when compared to higher n plus L value. Suppose if n plus L values are equal, then electron enter into lower n value subshell. Yes, I can example n plus L value 1 plus 0 1, 2 plus 0 2, then electron enter into 2s complete field 2p and is less than 3s. Yes, verify these two. 2 plus 1, 3. 3 plus 0, 3. Both having 3 values, n plus L values are same. If n plus L values are same, then electron enter into lower n subshell, that is 2p. That is why after complete filling of electron 2p, then only electron into 3s. Yes, after filling of 3s, then electron enter into 3p. After filling of 3p, then electron enter into 4s instead of 3d. This is the crucial point. Yes, this is the point required here. After complete filling of electron 3p, the electron not enter into same. This is n value 3. Here also n value 3. But electron not enter into 3D subshell. First electron enter into 4s subshell. Because 4 plus 0 is n plus l value here. Here 3 plus 2, 5. N plus l value is 5. So n plus l value is the lowest. That subshell has the lowest energy. So 4s subshell has lowest energy. That means if any element has suppose electrons more than 20, then electron first enter into 4s. First electron into 4s. After filling of 4s, then only the electron enter into 3D. This is general Euler diagram. This is according to Euler diagram. Most of the elements follow this trend only. If some elements violates this above principle or Euler diagram, then that configuration is called exceptional configuration, anomalous configuration, different configuration from the others. What are that elements? What are that exceptional configuration elements? Now anybody says, can you explain? In 1A group, yes, there are so many elements are there. In a 1A group, how many elements? Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. In any element, any exception is there? No. There is no exception. In all elements, expected configuration is NS1 in the last electron. Same as it is, all elements follow NS1 configuration. Hydrogen, last shell, 1s1. Lithium, last shell, 2s1. Sodium, last shell, 3s1. Potassium, 4s1. Rubidium, 5s1. Cesium, 6s1. Francium, 7s1. That means there is no exceptional configuration in 1A group. So, all you know how many groups in the periodic table? Yes, there are 18 groups. Yes, how many groups? 18 groups are present in the periodic table. In 1A group, there is no exception. In 2A group, generally all elements electronic configuration is NS2. Yes, so if you observe the first element beryllium, whose configuration is 2s2. Beryllium electronic configuration is 2s2, last shell. The next element magnesium, 3s2. Beryllium, magnesium, calcium, strontium, barium, radium. All these elements in the last shell, the last electronic configuration is NS2. All these elements follow NS2 electronic configuration. There is no exception. Is it follow Abbo rule? All the elements in the 2A group? What is your answer? Yes. Yes, all the elements follow Abbo principle. There is no exception. Yes. Okay. Out of 18 groups, now I am discussing 1A group complete. No exception. 2A group complete. No exception. Now what is the next group in the long form of the periodic table? What is the next group? Yes. The next group is third group. That is our Babu. 3B. That is the 3B. Third group. 3B group. What are the elements present in third B group? Roman number is 3B, but Latin number 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 groups are there, in which the position of the group 3B group is 3. Number 3. Number 3. Yes? Okay. In 3B group, what are the elements? In 3B group, what are the elements? Yes. The first element is scandium. And the next element is yttrium. Next element is lanthanum. So, scandium, yttrium, lanthanum, actinium. These are the elements in the 3B group. In 3B group. Now the first element scandium, is it any exception? In third B group? No. In third B group, the first element scandium, there is no exception. And the next element yttrium, there is no exception. Yes? Are you clearly observed? In 1A group, there is no exceptional electron configuration. If you expected Euler diagram n plus L rule, then as it is follows. For all the elements in 1A, for all the elements in 2A, in 3B scandium, okay, yttrium, okay. The next element is lanthanum. Next element is lanthanum. What is the expected configuration of lanthanum? Yes, I have already discussed. This is 3B group. This is 3B group and it is third group. In 3B group, the first element is scandium, it's okay. The next element is yttrium, it is also okay. The next element is lanthanum. Yes, its element does not follow open spell, not follow Euler diagram. What is the atomic number of lanthanum? Lanthanum atomic number is 57. Lanthanum atomic number is 57. I think all the members are know lanthanides. I am asking simple question. In a lanthanides, there are 14 elements are there. In which what is the position of lanthanum? In a lanthanides, yes, I am asking simple question. In the lanthanides, there are 14 elements. In which what is the position of lanthanum? At which position it is present? First position, second position, third position, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th. In this 14th position, at which place the lanthanum is present? So what is your answer? Yes, majority members think like this. Sir, it is the first position. No. Lanthanum is not the first element. Lanthanum is not the first element in lanthanide. After lanthanum, the remaining 14 elements are called lanthanides. Lanthanum is not a lanthanide. After lanthanum, the succeeding elements are called lanthanides. Okay, that is the observation in the case of lanthanum. So that means lanthanum is not a F block element. Lanthanum is not a F block element. Lanthanum is not a F block. Yes. So lanthanum is which block? Yes, that is the question. Yes, the expected configuration is 57. Electrons are 57 electrons. Yes, up to xenon, 54 electrons are completed. Up to xenon, 54 electrons are completed. After 54, the next electron, 55th electron, 55 electron. Actually, 55 atomic number goes to 55 atomic number goes to cesium. 55, 6s1. 6s2, barium. Next, after completing of the electron 6s2, expecting order is, as after this one, 3d. After this, 3d and so on and so on. After filling of 6s electron, next enter into 4f, next enter into 5d. Because 6 plus 0, 6, 4 plus 3, 7, 5 plus 2, 7. If n plus l values are equal, then the electron enter into 4f, lower n value. Therefore, in lanthanum expected electronic configuration is 6s2, 4f1. We are expecting 4f1. Suppose the lanthanum, the last electron, last entering electron also called, it is also called differentiating electron. Last entering electron, it is also called a differentiating electron. So, if a differentiating electron enter into s orbital, that belongs to s block. If a differentiating electron enter into p orbital, that belongs to p block. If a differentiating electron enter into d orbital, that belongs to d block. Here the differentiating electron enter into f orbital. Suppose if it is f orbital, then lanthanum is a block. Now is it lanthanum a block? No, we already explained lanthanum is not a block element. That means this configuration is wrong. So therefore expected is 4f1, but the observed 4f is 0 and the electron is 5d1. That is why this is the anomalous configuration. Exceptional configuration. So like that, there are so many elements in the periodic table having exceptional configuration. Yesterday class, in this class I am discussing about that exceptional configuration elements. Yes, okay. Yes, this is the first element, lanthanum. After completion of lanthanum, then the next element ever. After completion of lanthanum, the next element is actinium. Yes, so what is the electronic configuration again? 89, 57 plus 32, 2 plus 7, 9, 5 plus 3, 8, 89. That is actinium. Yes, here also xenon, 86, radon, 86. Radon 86 is completed. Then, and proceed. Under continuation, radon 86. Then electron enter into 7s2. Expecting is 5f1 and expecting is 60. But here the electron enter into 5f0, 61. Again, actinium also belongs to D block. Actinium also enter into D block. Yes, majority members are confusing here. Majority members are confusing. Sorry, in lanthanum, last electron present in 6s, sir. Last electron present in 6s, sir. But differentiating electron enter into D, sir. Then lanthanum D block or S block, sir? Yes, that I already explained. Last shell electron can't be explained black. Last entering electron, that is the important point. Last entering electron is called differentiating electron. Suppose in a classroom, one by one enter to the classroom at the starting of the class every day. Okay, so there are, suppose, nearly 30 members are there in class. So 30 members one by one are coming. Suppose 30th member, that is the last member, he is entering into the classroom and sitting on the last bench. Is it compulsory sitting on the last bench? No. That last entering member maybe sit on the first bench or second bench, third bench, fourth bench, fifth bench, whatever it is. So last enter member is important. Last entering member is called differentiating. So differentiating electron enter into 5D. Differentiating electron enter into 5D. Differentiating electron enter into 5D. That is why lanthanum is a D block but not S block. Actually, the last electron is 6s. Last bench member is S, but last entering member is sitting on D. Therefore, lanthanum is a D block. That is the very important point. How the lanthanum is a D block? Sir, in lanthanum last electron enter in S, sir. But how lanthanum is D block? S lanthanum, the electron enter into 5D. Of course, actinium also the last entering electron enter into D block. That is why lanthanum is a D block element. Actinium is also D block element. After lanthanum, 14 elements are lanthanides. After actinium, the 14 elements are actinides. Now I am asking one question. Sir, is it any exception in lanthanides, sir? In lanthanides, is it any exception? Is it an exception in actinides? Yes, that can be explained now. Yes. The exceptional electronic configurations. Exceptional configuration in lanthanides. Yeah, so we know lanthanides are 14 elements. in which the first element is cerium, presidium, neodymium, promethium, and so on, samarium, europium, gadolinium, and so on. The last element belongs to, last but one is yttrium. Before that, thulium. Last element, lutetium. In these 14 elements, how many elements are in exceptional configurations? Yes, there are just 2 elements. One is cerium, another one is gadolinium. Yes, what you are expecting configuration? Yes, my expectation is, sir, my expectation, sir. What is the atomic number of cerium, sir? 58. Oh, 58. Then already 54 atomic number belongs to xenon. That means noble gas configuration. After filling of noble gas, then electron enter into 6s2. 6s2. Because 54, this is 58. This is already filled 54 plus 4. This is total 4. After filling of 54, the electron entered to 6s2. After filling of 6s, according to Moeller diagram, the electron actually enter into 4f. But some electron here, actual electrons are 4. After 6s, the electron enter into 4f2 actually. But here 4f contain only one electron, 5d contain one electron. That is why it is exceptional configuration. D also contain one electron. 5d. 5d also contain one electron. In case of cerium. So therefore cerium is the first F block element, lanthanide. This is the first element in lanthanides. Atomic number 58 to 71 are called lanthanide. This is the first element, cerium, the lanthanide. Yes, after that cerium. After that cerium. Cerium next, yes, this is 5d1. Next element, actually next element, that is presidium, you are expecting is 5d1 as it is, next 4f2. But next element configuration is 4f3, presidium. Next element, neodymium configuration, 4f4, next 4f5, next 4f6, next 4f7. 4f7 belongs to europium. That is atomic number 63. Gadolinium also having 4f7 configuration. But one electron in deception. So, gadolinium in +3 oxidation state, it has half-filled exceptional configuration. It is stable. Cerium in +4 oxidation state, it has noble gas configuration. It is stable. So therefore, this is the exceptional configuration. Now I am introducing one point here. Europium and gadolinium both having F7 configuration. Sir, how, sir? Both having F7. Yes, how it is possible, sir? Europium F7 configuration, sir. That means gadolinium F8, sir. But how it is F7? Yes, europium configuration is 6s2 4f7. There is no 5d electron. But in the case of gadolinium, the electron enter into 6s2 4f7, one electron enter into 5d. That is why both having F7 configuration. Same manner, after completion of gadolinium, the next element 65, 66, 67, 68, 69, 70 is yttrium. Yttrium configuration 4f14. The last element lutetium also 4f14. Sir, yttrium, lutetium both having 4f14, sir. How it is, sir, once again? Yes, if yttrium configuration is 4f14, 6s2. In the case of lutetium, the configuration is 6s2, 5d1, 4f14. But it is not exceptional configuration. Why? After complete filling of 6s, then electron enter into 4f. After complete filling of 4f14 only, then electron 1 is present in D shell. So 5d1. But last electron actually 4f is present. That is why it is called a block element. Lutetium is a block. Last electron enter into F only. So whatever it is, it follow Euler diagram as per trend in case of lutetium. That is why these two are the exceptional configuration in throughout lanthanides. Ytterbium is not exceptional. It has F14 configuration as you are expecting. So as it is ytterbium, lutetium, same configuration. Okay, is it clear? So next we are discussing actinides. Yes. Again, exceptional electronic configuration in actinides. Exceptional electronic configuration. Yes, what is the exceptional configuration? Thorium atomic number. I have already introduced atomic number 89, actinium. Actinium, atomic number 89 is actinium. After actinium, the 14 elements are called actinides. Therefore, the first element is thorium. Thorium atomic number 90. You are expecting radon 86 noble gas. Then 7s2. After 7s2, expecting is 5f1, 5f1, but not filled in the case of actinium. 5d, 6d1 is filled up. But in the case of thorium also, we are expecting is 6d1, 5f1 thorium. That is a very, very important. Even though F electron is absent, but thorium is a black element. That is the special of thorium. In entire all F block elements, in case of lanthanides and in the case of actinides, that must contain, for example, in the case of lanthanide, all 14 elements having 4f electron at least one. In the case of actinide, all actinides contain 5f electron at least one. But there is no F electron, but thorium is a black element. That is a question. So thorium is a black element, but here there is no F electron. That is why it is exceptional configuration. So purple configuration, ultimate. Thorium has no F electron. Even though there is no F electron, it is a black element. After that, in thorium, some oxidation state, suppose in a +3 oxidation state, thorium has one F electron in +3 oxidation state. So now, protactinium, uranium, thorium atomic number 90. After that, protactinium 91. You are expecting is 60 to 5f1. But suppose if it is 5f1, then this one is 5f2. Yes, this is actually 5f2. Second element of actinides, protactinium 5f2, 6d1. That is why it is exceptional. Next element, uranium 92. Yes, this is 5f3, 6d1, 7s2. Next, yes, what is the special of first three elements in actinides? What is the special of first three elements in actinides? Yes, the special is these three are natural radioactive elements. Actually, all actinides are radioactive. All actinides are radioactive. But in these actinides, 14, first three are natural radioactive elements. That means after uranium, all elements are man-made elements, artificial radioactive elements. So up to natural, from thorium to uranium, three are exception. Of course, in artificial, the first element neptunium also some exception is there. Yes, the configuration of neptunium is yes, this is 7s2. This is 7s2. Yes, I can write top. 1 second. Yes. The electronic configuration of neptunium, exceptional configuration, is radon 86. This is 93. So first element 90, exception. 91, exception. 92, exception. 93 also exception. Atomic number 93, neptunium. After filling of 7s2, the electron enter into 6d1, then enter into 5f4. Yes, after filling of 5f4, the next element of plutonium. Plutonium, the electronic configuration of plutonium we are expecting is 5f5, 5f5, but 6d1. But actually, plutonium has no d electron, 6d electron. So therefore, 5f6 plutonium. Next, americium. Americium, the next element is americium. The next element atomic number 94 is plutonium, 95 is americium. Americium has F7 configuration like europium. In 4f block, the atomic number 63, europium configuration is 4f7, 6s2. Same americium also 5f7, 7s2. There is no 6d electron. But after that, after europium, the next element also 4f7. Europium is 4f7, 6s2. Gadolinium also 4f7, 6s2, but 5d 1 electron is there. Same situation in actinides also. Americium 5f7, 6d 0, 7s2. Later the next element atomic number 96, that is curium. Curium. So then 96, radon 86, 5f7, 6d1. So americium and curium both having same number of f electrons. Yes, I'm asking a simple question. How many f electrons present in curium? How many f electrons present in curium? What is your answer? How many f electrons present in curium? Yes. Majority members' answer is 7. But the answer is 21. Answer is 21. Why? In curium, the atomic number is 96. 5f electrons are 7. 5f electrons filling only take place after filling of 4f electron. That means in curium electronic configuration from 1s2, 2s2, 2p6, 3s2 like that, 4f14 is filled. After then 5f7. 14 plus 7, 21 electrons are present in curium f electrons. By good information, same number of f electrons also present in the net before that element. Before that the element is 94 is plutonium, 95 is americium. Americium also same number of f electrons like curium. But what is the difference? That has f7. This also f7. But it has no d electron. Here 1 d electron. That is the difference. Is it clear? Yes, after that 97 berkelium. So therefore then we are expecting 61. No 6d electron. No 6d electron. Therefore 4f 9. Berkelium. 98 californium. 99 einsteinium. 100 fermium. 101. 101, 102, 101 mendelevium, 102 nobelium, 103 lawrencium. Nobelium also 4f14, lawrencium also 5f14, lawrencium also 5f14. The difference is 5f14, 61 is there in the case of last element lawrencium. But finally, what are the exceptional configurations in actinides? In the lanthanides only 2 elements are exceptional. In actinides, there are 5 elements are exceptional. First 3, next 4, first 4, and the next middle one, curium. These are the exceptional electron configuration of actinides. This is about today's class. In next class, I am discussing some of the exceptional configurations of D block also. And later, I am introduced the very important mechanism. This is totally discussed about your upcoming examination, that is IIT mains, third mains and fourth mains for IIT advanced also. So for IIT advanced in organic chemistry, there is very important mechanism is there in alcohols. that is the pinnacle rearrangement. That mechanism can be explained in next class. Okay, so please subscribe my video to get more videos. Those members are ready to prepare for IIT advanced point of view. From today onwards, I will introduce every day. Today onwards, I introduce every day some new class related to IIT advanced. So, if you want that type of videos for IIT advanced related chemistry, so please subscribe these videos. Okay.